In this online lecture, we're going to discuss the basics of IR spectroscopy. We're going to see how the machine operates and how it delivers its data. And our key points are, number one, we're going to see different functional groups bend, stretch, and wag at different frequencies. We're also going to learn that, two, a functional group will absorb light if the frequency of light matches the frequency of stretching, bending, or wagging. This is going to be our most important key point. This is the basics of how the IR machine functions. And lastly, what we're going to see here is that, three, IR spectra show absorption bands that enable to determine if a certain functional group or groups are present in a molecule. So let's see how this works. What you see here is the molecule formaldehyde. And formaldehyde just so happens to have something called a carbonyl functional group. That is simply the C that's doubly bonded to the O. We call that a carbonyl functional group. What we need to understand is that if you actually have a sample of formaldehyde, it's not static like what you see here. For instance, let's represent the oxygen right here as some kind of sphere and the carbon also as some kind of sphere. And the double bond between them, let's represent it as this single bond right here. If you were to actually see a formaldehyde molecule, you would actually see the carbonyl bond do something like this. It would actually stretch and compress like this, almost as if there is a spring between the carbon and the oxygen. But that's not the only thing this carbonyl can do. It can actually do something like this, move back and forth like this. In organic chemistry, we call that wagging, kind of like the tail of a dog. So this is the reality of the carbonyl group in formaldehyde. What we've seen is that it can stretch, or have what's called a stretching vibration. And let's do this. Let's make up a number. Let's just say it happens to stretch at a frequency of 2 hertz. Now, what does that mean here? Remember, hertz is a measure of cycles per second. So if this is stretching at 2 hertz, it basically means this right here. Let's say we start at this position. The 2 hertz means that it'll stretch 1 like this, and then 2 cycles per every second. Now, keep in mind that's not the reality. It actually vibrates at a much, much higher frequency, but let's keep the number simple for now. And also, just a side note here, of course the vibrations would be temperature dependent, but let's just assume room temperature for our example. Now, let's say we could also measure the wagging. And let's happen to say that it wags at 4 hertz, which again, it means it goes back and forth 1 cycle, or wags back and forth, 4 times per 1 second. If that's the reality, then let's see what happens when we take our formaldehyde molecule and we stick him in the IR spectrometer. And let's again label our stretchings at 2 hertz and our waggings at 4 hertz. So here is how the IR spectrometer functions. What happens is when the molecule is in the machine, we take something like this, a light source, which is simply something that has the ability to shine light at a molecule at various frequencies. On the other side of the machine, we have this thing right here, a detector. And all he can do is detect light. Now, imagine this for a second. Let's say again, our light source has the ability to produce light at various frequencies. So let's say we set our light source to deliver a light that happens to have a 1 hertz frequency. If we shine this 1 hertz frequency light at our molecule, it'll go right through the molecule and hit the detector. And the detector, of course, would say, when you shine 1 hertz frequency light at the molecule, I detected it. We'll see why that happened in a second. But for now, let's graph what we see in front of us here. If you had a graph with, let's say, on the y-axis, the percent transmitted, and this means the percent of light that transmits or moves through the molecule, which would obviously run from 0 to 100%. And let's say for now on the x-axis you put the frequency of light. So the graph of what we just saw here would look like this. At 1 hertz frequency light, 100% of the light went through the sample and the detector detected that light. Now, let's see what happens if we go back to our light source, and now let's set it at 2 Hz frequency light. If we shine this at the molecule, what's going to happen here is the molecule will actually absorb light at that frequency. And this right here is key to understanding how this machine works. Notice the frequency of the light that's being absorbed, 2 in this case, matches the frequency of the stretching. When these two things match up, the molecule will absorb the light, which means think about the detector here. His observation is that when you shine 2 Hz frequency light, he doesn't detect the light at all because it was simply absorbed by the molecule. Let's see what this would look like on our graph now. Again, at 2 Hz frequency light, the detector would say not very much transmitted through it. A lot of it was absorbed, so we have a small percent that's transmitted. And that would be this point on the graph. Now, let's go back to our machine here. Let's now take our light source and set it at this time 3 Hz. Think about what we just learned here. If this molecule stretches at 2 Hz and wags at 4 Hz, then when we shine the 3 Hz frequency light, it should go right through it. There simply is no match in this case. And the detector therefore would say 100% of the light transmitted through the molecule. So again, going back to our graph right here, we would see that this would be the graph at 3 Hz frequency, 100% transmitted. Now, while we're here, let's do this. Let's connect these dots. This is what we would have. However, let's go back to our IR and let's talk about one more case here. What if we set the light source this time to 4 Hz frequency light? If you've been following along, since this molecule does wag at 4 Hz, then we should expect this light to be absorbed by the molecule. But just to let you know, in some cases, not all of the light is absorbed. And let's just pretend for this case, even though it wags at 4 Hz and it does absorb the 4 Hz frequency light, some of it actually does eventually get through. This happens sometimes in the IR, which means, let's go back to our graph here. If we were to graph this point at 4 Hz, let's say this much percent passes through, which means we would get this point on the graph. And again, let's connect these dots. We'd end up with something that looks like this. What you're seeing here in front of you is basically what the IR machine spits out when you put a sample molecule in the machine. And the vocab here is this. We would call these simply absorption bands. Think about where that term is coming from. It is at these points that light is being absorbed by the sample molecule in the machine. And think about what this means for us. Remember, all carbons and oxygens are the same. And all carbons doubly bonded to oxygens are the same as well. This means that if any sample we put in the IR machine, as long as we run it, let's say, at room temperature, and if the molecule happens to have a carbonyl group, it's going to stretch and wag at 2 and 4 Hz, no matter what molecule it happens to be in. Which means this, if we do run a sample molecule through the IR, and we see absorption bands at 2 and 4, we're going to know without a doubt that our molecule has a carbonyl functional group. Because it's only carbonyls that stretch and wag at those particular frequencies. For instance, it's safe to assume that, let's say, if the carbon were singly bonded to the oxygen, remember single bonds are longer than double bonds. So you can think of that single bond as being a different type of quote-unquote spring than the double bond. Which means if your molecule had a C singly bonded to an oxygen, that bond would stretch and wag at different frequencies than the C double bonded to the O, and would therefore have its own unique absorption bands. So notice what the IR helps us figure out. It simply helps us determine what functional groups that might be present in a molecule. However, let's look at an actual IR spectrum. This right here is the real deal. Notice on the y-axis here you do have the same thing, the percent transmitted. And notice we also have absorption bands that look like this. Sometimes they're broad like this here, sometimes they're narrow, and sometimes they're, well, in between. But what I want to point out here is that In the actual IR spectrum, they don't put frequency on the x-axis, they put wave number instead. There's a good reason for this, but it's beyond this lecture at this point. Just know for now that there is a connection between frequency of light and wave number of light. And instead of thinking that absorption bands happen at certain frequencies, we can say absorption bands also happen at certain wave numbers. And just in case, let's know these wave numbers typically on the chart run from 4,000 all the way to 0. Some other basics about the IR spectrum here. Let's know that right about here, from 1800-ish to 4000, is what's called the functional group region. This is where we're going to look for absorption bands that signal certain types of functional groups in the molecule. And the other side of this region right here is called the fingerprint region. We're going to see that certain molecules have certain absorption bands in this region, and those bands can act almost as fingerprints, meaning that every type of molecule in organic chemistry has a specific fingerprint region with its corresponding absorption bands that are unique to that molecule. Now remember here, the whole basis of the IR machine, again, is that certain functional groups correspond to certain absorption bands at given wave numbers. And thankfully, the scientists got together and figured out the wave number for all possible functional groups in organic chemistry. Notice this chart here. It's the functional group wave numbers. Let me show you how this chart is read. Notice on the left-hand side we have bond. So if you're looking at the OH bond, if our molecule was an alcohol and therefore had an OH bond, we would expect to see an absorption band in roughly the 3,200 to 3,650 region. And the intensity of that band, which is basically how strong the signal is, would be very strong and broad. We'll see what this looks like in another online lecture. For now, I just want you to know that a chart does exist with all the functional groups and their corresponding wave numbers. And think about how valuable this information is. If we're trying to figure out what a substance is, a great place to start is what functional groups are present in the molecule. The IR spectrum is going to deliver that information. However, there's one more thing I want to talk about here. Remember, we saw with our carbonyl example that it technically had two absorption bands, one for the stretching and one for the wagging. As we progress through the IR material, we're going to see that functional groups can have many absorption bands. And let's see why here for a second. For instance, a typical molecule in organic chemistry has CH bonds in it. Let's look at the different ways that these bonds can vibrate. For this particular case, one option is you can have something called symmetrical stretching. Another type of vibration here, you could also have something called asymmetrical stretching. Sometimes the bonds can even do this, something called scissoring. And the bonds can also do this, which they call rocking. And it can also get very three-dimensional. This is obviously hard to see here, but these hydrogens can actually twist out of plane, which means from our point of view, the hydrogens would move out towards us. And therefore, the hydrogens would now be not in the same plane as the carbon. Or they can even wag out of plane. We're going to see that a lot of these vibrations have their own corresponding absorption band on the IR spectrum. If we want to do a very detailed analysis on an unknown molecule, then we'd want to look at these other types of vibrations. But if we want to know simply if a molecule has a certain functional group, we can usually get by just looking at only one of the possible vibrations and trying to find its corresponding absorption band on the IR spectrum. Remember, this is just an introduction to IR. We're going to go into a lot more detail in other online lectures concerning this machine. However, what did we learn so far here? Key points. We saw that number one, different functional groups bend, stretch, and wag at different frequencies. And number two, the most important one here, A functional group will absorb light if the frequency of light matches the frequency of the stretching, bending, or wagging. And we saw number 3 here, IR spectrum show absorption bands that enable to determine if a certain functional group or groups are present in a molecule.